So this is acids and bases. We're going to try to explain some of the more difficult topics. So here we're basically just going to explain where the equilibrium expression came from. So if you have some acid, general acid, we'll just call it HA, the concentration of HA is going to be proportional to the product of how much A minus you have and H plus you have, because the more of those two there are, the more collisions you're going to get between the two, and so then the more HA you're going to form. So basically, stated mathematically, HA is proportional to the product of those two concentrations. So yeah, that's the proportional symbol. So if something's proportional to something else, that means it's equal to some constant times that. So that's your constant of proportionality. So then you can just rearrange the terms. So if you divide both sides by HA and then divide both sides by C, you get 1 over C equals that. And then what do you know? That on the right is just the equilibrium expression, and then 1 over C, you can just rename that as Ka. So that's basically where the equilibrium expression came from. So now we're going to talk about the basic idea of what a buffer is, and we're going to use the example of weak acids as buffers. You could also have weak bases as buffers, but we're just going to go through weak acids, and then the same concept applies for weak bases. You just flip acid and base. So this Ka has to be less than 1, the weak acid that is, to make a buffer solution. So what a buffer really is that it means that once you've made the solution, if you add a small amount of a strong base or strong acid, the pH is not going to change much, because essentially the weak acid sort of absorbs the blow of that strong base or acid, is maybe a way to think about it. And that's sort of why, basically, if you look at the titration curve, there's a region where it flattens out. And in that region there's about as much HA as A minus. So basically, whether you add a strong acid or a strong base, the H plus or OH minus can be neutralized by either HA or A minus. Alright, so we're going to start out this titration with just a weak acid. The weak acid doesn't dissociate very much, but we're going to want to have a high concentration of it to make an effective buffer, so the pH is still pretty low. So there could be an example image of the titration curve, and the red dot shows that we're at the start of the curve right now. We're going to add a little bit of the strong base, it'll dissociate and then neutralize the H+, so the pH is going to go up, it will not go up as much as it would have were there no weak acid present, because the weak acid is going to make more H+ to make up for that loss. Eventually the half equivalence point is reached after enough strong base has been added. At that point the solution's fully buffered, so it could buffer either a strong acid or a strong base, because the concentration of HA is equal to the concentration of A minus at that point. So pH is also equal to pKa, so there it's at the half equivalence point. We can continue to add strong base until the equivalence point's reached. At that point, all the HA is gone. It's all dissociated into A minus and H+, and a lot of that H+ has been neutralized, which is why the pH at equivalence point is greater than 7. But that's also because mainly the Na+, if we're assuming NaOH is a strong base, is not going to accept OH minus, but the A minus of the HA will accept H+. So there we're at the equivalence point, and if you continue to add strong base after that, the pH is going to increase logarithmically, which is what you would expect if there were no weak acid there, because its pH is a log scale. Alright, so we're going to explain the Henderson-Hasselbalch equation. It's actually nothing more than the equilibrium expression with the terms rearranged. So if you're really good at working with logs, you don't have to memorize it. But even if you are, maybe just to save time, you might want to memorize it. But either way, here's where it comes from. So we're going to start with the equilibrium expression. You take the negative log of both sides. Now what I'm actually going to do is I'm going to take out the negative. You'll see why I did this later. I haven't changed anything on either side. Now, basically using properties of logs, I can split the log up like this. I redistribute my negative. Now I reintroduce my p notation. Now I add that log term to both sides. And now you can see I just flip the things on either side of the equal sign. I didn't change anything here, and that's, what do you know, the Henderson-Hasselbalch equation. So it's just the same as the equilibrium expression. And that's the end.